Look up at the night sky on a clear evening, and you'll see countless points of light, each a sun, a world, or a distant galaxy. But among those familiar patterns, one world stands apart, not for its brightness, but for its profound strangeness, a planet so unusual it defies nearly every convention of our solar system. This is Uranus, the ice giant, a world tilted completely on its side, spinning like a top knocked over, a cosmic anomaly hiding in plain sight. For centuries, it was little more than a faint, wandering star to early astronomers, but today we know it as one of the most mysterious and least understood planets orbiting our sun. Think about that for a moment, a world where the sun rises in the north and sets in the south, where a single season lasts for decades, and where the very laws of planetary behavior seem to have been rewritten. What catastrophic event could have knocked a whole planet onto its side? What secrets lie buried beneath its serene, blue-green atmosphere? The answers to these questions don't just change our understanding of Uranus, they reshape our entire story of how planetary systems form and evolve. This voyage of discovery is what awaits us today, as we embark on an exploration to unravel 25 of the most baffling and compelling mysteries of this distant ice giant. We will journey from its chaotic, storm-racked cloud tops down into its hypothesized, slushy interior, and out to its intricate system of rings and moons, each with a story to tell. We'll confront the puzzle of its lopsided and wildly off-center magnetic field, a magnetic bubble that seems to stutter and flicker in ways that physics struggles to explain. We'll investigate the startling cold of its atmosphere, the coldest place in the solar system, and ask why this giant world holds onto such a deep, profound chill. And we'll peer into the enigmatic compositions of its moons, worlds like Miranda, with its sheer cliff faces taller than Mount Everest, and Titania, which may hide a vast subsurface ocean. Each mystery is a piece of a grander cosmic puzzle, a clue that brings us closer to understanding not just Uranus, but the turbulent, violent, and beautiful processes that built our celestial neighborhood. So prepare yourself for a deep space adventure that will challenge everything you thought you knew about the outer solar system. This is not a simple tour of facts and figures. It is a detective story written across the cosmos, a journey into the heart of an ice giant that has kept its greatest secrets locked away for billions of years. As we count down these 25 unexplained marvels, you will witness a world of profound contradictions, a planet both serene and violent, familiar and utterly alien. Let's begin our descent into the unknown to decode the enigma that is Uranus. And so we arrive at the very first and perhaps most defining mystery of this distant world. Uranus is a planet that has literally been knocked on its side. Picture in your mind the other planets in our solar system, all spinning like tops with their poles pointing more or less up and down relative to the plane of their orbit around the sun. Now erase that image and replace it with Uranus, a world that rolls around the sun like a giant marble, its rotational axis tilted a staggering 98 degrees. This isn't just a slight lean, it's a complete reorientation. For a significant portion of its long, 84-year orbit, one pole is pointed directly at the sun, bathing that entire hemisphere in constant daylight, while the other pole is plunged into a deep, frigid night that lasts for decades. The immediate and most compelling question is, what tremendous force could have caused such a dramatic shift? How does an entire planet get tipped over? The prevailing theory among astronomers points to a truly violent birth for our solar system, a time often called the Late Heavy Bombardment, when protoplanets and debris were still crashing into one another. The leading hypothesis suggests that a cataclysmic collision with an object roughly the size of Earth struck Uranus a glancing blow in its youth. This wasn't a head-on impact that would have shattered the planet, but a massive, side-swiping event that delivered an immense torque, effectively pushing the entire world onto its new, sideways axis. Think of it as a cosmic billiard ball struck with unimaginable force, forever altering its spin. This single ancient event didn't just change its orientation, it completely rewrote the rulebook for the planet's climate and weather. With such an extreme tilt, the concept of seasons on Uranus becomes something out of science fiction. On Earth, our relatively modest tilt gives us the gentle, predictable transition from spring to summer, fall to winter. On Uranus, a season is a 42-year-long extreme. As one pole faces the sun, it receives a massive, continuous influx of solar energy, potentially stirring up colossal storm systems in its atmosphere. Then, as the planet continues its slow roll, that pole moves into shadow, and the entire hemisphere undergoes the most profound deep freeze in the solar system, with temperatures plummeting as atmospheric gases may even snow out. This radical seasonal cycle, a direct result of the tilt, creates a world of atmospheric behavior we are only beginning to comprehend. The collision theory offers a clean, dramatic explanation, but it also raises new puzzles. Why didn't the impact strip away Uranus's atmosphere? Or why does its system of rings and moons also share this tilted orientation? This first great mystery sets the stage for all the others, a foundational event that made Uranus the profoundly strange world we gaze upon today. Moving from the planet's bizarre tilt, we encounter another celestial feature that seems almost designed to evade our gaze: the faint, mysterious ring system of Uranus. Unlike the spectacular, brilliant bands of ice that define Saturn, the rings of Uranus are dark, narrow, and incredibly difficult to detect. For nearly 2 centuries after the planet's discovery, we had no idea they even existed. They were only found by sheer accident in 1977, when astronomers watching Uranus pass in front of a distant star saw the star flicker not just as the planet moved in front, but several times both before and after. This repeated blinking revealed the presence of multiple thin, dark rings blocking the starlight, a discovery that completely changed our understanding of the outer solar system. Today, we know of at least 13 distinct rings encircling the ice giant, with the possibility of even more faint, dusty bands nestled between them. But the central puzzle remains: why are they so profoundly dark? The leading theory suggests they are composed of a mixture of water ice and vast amounts of dark, carbon-rich material. This isn't the pristine, reflective ice you might picture. Out in the frigid environment around Uranus, this ice is constantly bombarded by high-energy radiation, which acts like a cosmic tanning bed, chemically altering simple ices and organic compounds into a dark, sooty substance often called radiation-darkened tholins. Think of it as a kind of cosmic charcoal, absorbing light instead of reflecting it, rendering the rings nearly black. This composition makes them astronomically challenging to observe. They don't shine with reflected sunlight like Saturn's rings, but instead are often detected by the starlight they block or the faint thermal glow they emit. The origin of these shadowy loops is a subject of intense debate. One compelling idea is that they are the shattered remains of a small moon or several moons that ventured too close to Uranus and were torn apart by its immense gravitational pull. Another possibility is that they are leftover building blocks from the planet's formation, material that never managed to coalesce into a larger moon. Their stark difference from Saturn's system raises profound questions about planetary evolution. Saturn's rings are bright because they are constantly being refreshed and recoated with fresh, clean ice, perhaps from icy geysers on its moon Enceladus. Uranus's rings, by contrast, appear old, static, and untouched by such rejuvenating processes. They are a relic of a more violent past, their dark material a testament to eons of relentless radiation exposure. This makes them a frozen archaeological record, preserving clues about the chaotic early days of the Uranian system, a time of colossal impacts and gravitational upheavals that shaped the entire region. But if you think a sideways spin is peculiar, just wait until you encounter the third great mystery: the chaotic and deeply skewed magnetic field of Uranus. On Earth, our magnetic field behaves in a relatively straightforward manner. It's generated by the churning of molten iron in the outer core, and its poles align fairly closely with our planet's geographic poles of rotation. This gives us a reliable north and south magnetic pole, which is why our compasses point north so consistently. Uranus, however, plays by a completely different set of rules. Its magnetic field is not centered on the planet's core, but is instead offset by nearly a third of the planet's radius. To put that in perspective, if Earth had a similarly lopsided field, the magnetic North Pole would be located somewhere over Central Asia instead of the Arctic. This is just the beginning of the strangeness. Not only is the field off-center, but its axis is also tilted an astonishing 59 degrees away from the planet's rotational axis. This creates a magnetic environment unlike any other. As Uranus rolls along on its side, this wildly tilted and offset magnetic field wobbles dramatically with each rotation. Imagine a poorly balanced top spinning and shuddering as it moves. That's the Uranian magnetosphere. For any spacecraft passing through, the magnetic field wouldn't feel like a steady, protective bubble, but more like a flickering, stuttering force field that changes intensity and direction in a chaotic dance. So, what could possibly cause such an erratic magnetic field? The leading theory points to the planet's unusual internal structure. Scientists hypothesize that deep within Uranus, beneath its thick atmosphere of hydrogen and helium, lies a vast slushy ocean. This isn't an ocean of water as we know it on Earth's surface, but a high-pressure, superheated fluid composed of water, ammonia, and other ices. In this exotic state, the material can conduct electricity, and it's the motion within this conductive layer, a process called a dynamo, that is thought to generate the planet's magnetic field. However, because this dynamo is occurring in a relatively shallow, slushy shell rather than a deep, well-organized molten core, the resulting magnetic field is messy, complex, and prone to flipping. It's as if the planet's internal compass is broken, generating a field that is fundamentally unstable. This bizarre magnetic configuration has profound consequences. It means that Uranus's auroras are not neat circles around its poles, but are instead smeared and distorted across its atmosphere. It also suggests that the interior of this ice giant is far more dynamic and strangely layered than we ever imagined. A world where the very forces that define a planet's magnetic personality are born from a churning, icy sea. If the planet's tilted axis and lopsided magnetic field seem strange, wait until you experience a single season on Uranus, a season that lasts for over 2 decades. This is the fourth great mystery, the world's extreme seasonal swings. Here, the concept of a year takes on a chilling new meaning. Because Uranus takes 84 Earth years to complete a single orbit around the Sun, and its axis is tilted almost perfectly onto its side, each of its 4 seasons lasts for roughly 21 of our years. For a quarter of its orbital journey, one hemisphere is bathed in uninterrupted sunlight, a continuous 42-year-long summer day, while the opposite hemisphere endures a winter night of equal length, a darkness so profound and prolonged it's almost impossible to comprehend. Now consider what this does to the planet's atmosphere and climate systems. On Earth, the daily cycle of sunrise and sunset acts as a vital regulator, consistently distributing solar energy and helping to stabilize our weather. Uranus has no such rhythm during its solstices. For those long decades, the pole facing the Sun receives a relentless, direct blast of solar radiation. You might expect this to make the planet incredibly hot, but the reality is far more counterintuitive. Despite receiving 24 hours of sunlight for years, the sunlit pole doesn't become a scorching desert. In fact, measurements from the Voyager 2 flyby and subsequent Earth-based observations reveal something startling. During the height of summer, the sunlit pole is often no warmer and sometimes is even colder than the equatorial regions. This bizarre temperature inversion completely defies our basic expectations of how a planetary atmosphere should behave. The explanation for this unexpected chill lies in the planet's peculiar energy budget and its sluggish atmospheric response. Uranus, for reasons still not fully understood, has an exceptionally low internal heat source, unlike its cousin Neptune, which glows with internal warmth. This means Uranus is almost entirely reliant on the faint and distant sun for its energy. Its atmosphere, composed mostly of hydrogen, helium, and methane, is so vast and lethargic that it cannot efficiently transport and distribute the solar heat it receives. The energy from the sun simply doesn't get circulated quickly enough from the day side to the night side, or from the pole to the equator. The result is a kind of atmospheric paralysis, where the pole under the midnight sun becomes a heat sink that struggles to warm up, while the dark side plunges into the deepest freeze in the solar system. The transition between these extreme seasons must be a period of extraordinary atmospheric chaos. As Uranus slowly moves from solstice to equinox, the sun finally rises over the frozen, dark hemisphere that has spent 21 years in total night. The sudden influx of solar energy likely triggers planet-wide convulsions, stirring up colossal storms, jet streams, and cloud formations that could dwarf the largest hurricanes on Earth. The Voyager 2 spacecraft glimpsed a relatively bland world, but it happened to be flying by during Uranian summer solstice, a time of atmospheric stagnation. More recent observations from the Hubble Space Telescope and powerful ground-based observatories have caught glimpses of a much more active Uranus during its equinoxes, with giant, bright storm clouds erupting across its face. This suggests that the planet's weather is not calm, but is instead a system of long, dormant periods punctuated by violent, seasonal outbursts when the shifting sunlight triggers a planetary-scale reorganization of its atmosphere. It is a climate of epic patience and sudden, violent upheaval, a direct and spectacular consequence of a world that rolls through the void on its side. As we peel back the layers of this distant world, we stumble upon a fifth mystery that cuts to the very heart of its frozen nature, the profound and puzzling lack of internal heat. Every giant planet in our solar system, from the swirling storms of Jupiter to the fierce winds of Neptune, radiates more energy into space than it receives from the sun. This excess energy is the planet's internal heat, a leftover from its violent formation, slowly released over billions of years and continually stirred by the sinking of dense materials through its interior. It's this internal engine that powers the most dramatic weather in the solar system. Uranus, however, stands as the lone exception. Measurements confirm it radiates almost no surplus heat at all. Its energy budget is virtually in balance, making it the solar system's coldest planetary atmosphere and suggesting a core that is strangely, eerily quiet. This heat deficit presents a major challenge to our understanding of how planets form and evolve. When the Voyager 2 spacecraft flew past in 1986, its instruments revealed a planet that was thermally lethargic. While Neptune, a near twin in size and composition, radiates about 2.6 times more heat than it gets from the sun, Uranus's output is barely 1.1 times the solar energy it absorbs. The difference is staggering. Imagine two houses built at the same time with the same materials. One is warm and cozy with a working furnace, while the other is cold and still, its heating system broken or never turned on. This is the fundamental puzzle of Uranus. Why is its internal furnace, which should have been roaring for billions of years, so silent? Scientists have proposed several compelling theories to explain this deep freeze. The most prominent hypothesis points back to the same colossal impact that may have tipped the planet on its side. The idea is that the impactor, perhaps an Earth-sized protoplanet, did more than just reorient Uranus. It may have essentially punched through the outer layers and blasted a significant portion of the planet's primordial heat into space. This catastrophic event could have left the interior stratified and stable, effectively shutting down the efficient convection that drives heat flow from the core to the upper atmosphere. Instead of a churning, dynamic interior that constantly brings hot material upward, Uranus's inside might be more like a layered, stagnant pond, with very little internal motion to transport warmth. Another possibility is that Uranus simply formed from colder, less energetic building blocks in the outer solar system, and some unique internal barrier, perhaps a layer of supersonic water or a composition that inhibits convection, prevents the residual heat from escaping. This lack of an internal engine has dramatic consequences for the planet's atmosphere. Without a strong internal heat source to drive convection from below, the Uranian weather system is largely at the mercy of the feeble and seasonally variable sunlight, leading to the sluggish yet periodically explosive climate we observe. The planet's profound cold is not just a curious fact, it is a fundamental clue that its history was far more violent and its internal structure far more peculiar than we ever imagined. Now, if the planet's missing heat and extreme seasons puzzle you, the mysteries only deepen as we plunge beneath its cloud tops to explore the sixth enigma, the bizarre composition of its hidden mantle. Beneath that serene, blue-green veil of hydrogen and helium lies a realm so alien it challenges the very definition of an ocean. This isn't a layer of gas like the interiors of Jupiter and Saturn. Instead, scientists believe Uranus contains a massive, superheated mantle composed primarily of water, ammonia, and methane ices. But here's the crucial twist. In the crushing pressures and scorching temperatures thousands of kilometers below the surface, these familiar substances are transformed into an exotic, electrically conductive fluid, a slushy sea that behaves like nothing we have on Earth. This hypothesized mantle is often called a supersonic water ice. Imagine taking a block of ice from your freezer and subjecting it to pressures over 1,000,000 times greater than Earth's atmosphere and temperatures of several thousand degrees. Under these extreme conditions, the water molecules break apart. The oxygen atoms lock into a rigid, crystalline lattice like a solid, while the hydrogen ions float freely through this structure, creating a form of matter that is both solid and liquid at the same time. It's a substance that can conduct electricity and generate magnetic fields, which directly ties it to the planet's lopsided and wildly tilted magnetosphere we discussed earlier. This isn't a placid, deep ocean. It's a churning, dynamic, and fundamentally strange layer of material that powers the planet's most inexplicable features. The existence of this exotic mantle is what solidifies Uranus's classification as an ice giant, a distinct category from the gas giants like Jupiter and Saturn. While Jupiter and Saturn are predominantly balls of hydrogen and helium all the way down to their relatively small cores, Uranus and Neptune are thought to be mostly composed of this superheated, icy slurry. Their rocky cores are believed to be relatively small, surrounded by this immense pressurized mantle that makes up the bulk of the planet's volume. This fundamental difference in composition likely stems from where they formed in the early solar system. Uranus and Neptune accreted further from the Sun, in a region cold enough for water, ammonia, and methane to condense into icy planetesimals. These frozen building blocks then came together to form the planetary core, which was only massive enough to attract a relatively thin envelope of hydrogen and helium gas. The result is a world that is, in essence, a massive pressurized ocean wrapped in a thin gaseous shell. Understanding the precise behavior and structure of this mantle is critical to solving many of Uranus's other puzzles. Its strange, sluggish convection, the way heat moves through it, could be the key to the planet's profound lack of internal heat. If the mantle is stratified into stable layers like oil floating on water, it could effectively trap the planet's primordial warmth deep in its interior, preventing it from escaping to the surface. Furthermore, the complex motions within this electrically conductive fluid are the prime suspect for generating that chaotic, off-center magnetic field. Unlike Earth's field, which is generated by the swirling of molten iron in a rotating sphere, the Uranian dynamo might be happening in a relatively shallow, uneven shell, leading to a magnetic field that flickers and wobbles in its uniquely bizarre way. Probing the secrets of this hidden, slushy interior isn't just about understanding one world. It's about reading the recipe for a whole class of planets that are among the most common in our galaxy. Venturing outward from the planet itself, we arrive at a realm of stunning complexity and drama, the mysterious collection of moons that orbit Uranus. With 27 known satellites, each one named for a character from the works of William Shakespeare or Alexander Pope, this system is a celestial stage set for some of the most bizarre geology in our solar system. The five largest Miranda, Ariel, Umbriel, Teutonia, and Oberon are not simple balls of ice and rock. They are individual worlds, each holding its own unique and often perplexing secrets, carved by forces we are only beginning to understand. Let's begin with the smallest and perhaps the most dramatic of the major moons, Miranda. When Voyager 2 flew past in 1986, it revealed a world that looked as though it had been shattered and hastily reassembled by a cosmic giant. Its surface is a chaotic patchwork of bizarre features, most notably the immense racetrack patterns known as coronae. These are vast, trapezoid-shaped regions of parallel ridges and valleys, some as wide as 200 kilometers, crisscrossing the landscape. One of the most famous Verona Rupes is a staggering cliff face estimated to be 20 kilometers high, making it the tallest known cliff in the solar system. If you were to stand at its top, the fall would last for nearly 12 minutes. The origin of this fractured, jumbled terrain is a subject of intense debate. One leading theory suggests that Miranda was torn apart by a titanic collision in its past, only for its own gravity to pull the fragments back together in a chaotic jumble. Another compelling idea is that powerful internal tidal heating, generated when Miranda was in a different, more eccentric orbit, caused its interior to partially melt and churn, forcing vast slabs of the crust to shift, crack, and overturn in a process called diapirism. Moving inward, we encounter Ariel, a moon that presents a stark contrast. Its surface is the youngest and brightest of the major moons, crisscrossed by an extensive network of huge, fluid-filled canyons and smooth plains. These vast chasms, some hundreds of kilometers long and several kilometers deep, suggest a world that was once geologically active. The smooth floors of these canyons appear to be resurfaced by a material that flowed like icy lava, likely a slushy mixture of water and ammonia that welled up from the moon's interior before freezing solid. This points to a past where Ariel possessed a warm, perhaps even liquid, subsurface layer that could breach the surface and erase older, cratered terrain. The question of what provided the heat to drive this activity remains. Was it the tug of Uranus's gravity creating internal friction, or did Ariel retain more of its primordial formation heat than its siblings? In stark opposition to bright Ariel is Umbriel, the dark sibling. This moon is one of the darkest objects in the solar system, its ancient, heavily cratered surface coated in a mysterious, uniformly dark material. It's as if the entire world has been blanketed in a layer of cosmic soot. While other moons show bright ice in fresh craters and on their poles, Umbriel offers almost no contrast, its most prominent feature being a single, bright ring on the floor of one crater, nicknamed the fluorescent Cheerio. The source of this pervasive darkness is a major puzzle. One possibility is that Umbriel is simply the oldest and least active of the moons, its surface having been darkened over billions of years by relentless bombardment from cosmic radiation, a process called space weathering. However, this doesn't fully explain why it is so much darker than its similarly aged neighbor, Oberon. Another fascinating theory is that the dark material was deposited from an external source, perhaps from the breakup of a dark, carbon-rich moon that once orbited Uranus, whose debris settled preferentially on Umbriel's leading face as it plowed through the cloud. Finally, we come to the two largest moons, Teutonia and Oberon. These worlds are giants in the Uranian system, each over 1,500 kilometers in diameter. Teutonia is marked by a massive canyon system that dwarfs Earth's Grand Canyon, suggesting it underwent significant global expansion as its interior froze and expanded in the distant past. Oberon, meanwhile, appears more ancient and battered, its surface pockmarked with craters and featuring mysterious dark material coating the floors of its largest impacts. Most intriguingly, scientists now speculate that both of these largest moons, along with possibly Ariel, could harbor deep, liquid water oceans beneath their icy crusts, kept from freezing by a combination of radioactive decay in their rocky cores and the antifreeze effect of dissolved ammonia. The potential for these hidden, subsurface oceans places them on the growing list of worlds in our solar system that could, in theory, offer niches for life, turning these distant, Shakespearean worlds into some of the most compelling targets for future exploration. Of all the strange worlds circling Uranus, none captures the imagination quite like the innermost of its major moons, Miranda. When the Voyager 2 probe returned its first close-up images in 1986, scientists were staring at a world that defied all geological logic. It was not a gently cratered ball of ice, but a chaotic patchwork of wildly different terrains, a global jigsaw puzzle where pieces from entirely different worlds seemed to have been forced together. One area would show ancient, heavily cratered highlands, speaking of a surface billions of years old. Right next to it would be a region of vast, smooth plains, as if an icy lava had recently flooded the landscape. And cutting across everything were those bizarre, trapezoid-shaped features known as coronae giant, ridged patterns that look like the tracks of a cosmic bulldozer. This is not the gentle geology of a moon that cooled quietly. This is the scarred face of a world that has endured apocalypse and rebirth on an unimaginable scale. The coronae are the centerpiece of Miranda's mystery. These are not simple cracks or canyons. They are immense, complex geological features, some spanning up to 300 kilometers across. They appear as series of parallel ridges and troughs, forming giant ovals or trapezoids that stand out starkly against the surrounding terrain. Imagine a vast, frozen racetrack etched into the surface with concentric grooves and bright, chevron-like patterns at their centers. The three most prominent are named Arden, Elsinore, and Inverness after locations in Shakespeare's plays. How does such a thing form on a moon only about 470 kilometers in diameter? The most compelling theories point to incredible internal forces. One leading idea is a process called diapirism, where a warmer, less dense material from the moon's interior slowly pushes up through the colder, brittle outer crust like a giant blister of ice. This upwelling would have deformed the surface, creating the concentric ridges and valleys we see today. The driving force for this activity could have been intense tidal heating in Miranda's past, when its orbit was more eccentric and the gravitational tug of war with Uranus created friction that warmed its interior to the point of geological rebellion. But the coronae are only part of the story. Miranda is also home to Verona Rupes, a cliff face so immense it holds the record for the tallest known cliff in the entire solar system. Estimates place its height at a staggering 20 kilometers, nearly 10 times the depth of the Grand Canyon. If you were to stand at its precipice, the fall to the bottom would last over 10 minutes in the moon's weak gravity. The existence of such a monumental feature suggests that Miranda was subjected to titanic stresses that cracked its crust on a global scale. This leads to the most dramatic hypothesis for the moon's fractured appearance, that Miranda was literally shattered to pieces by a colossal impact and then haphazardly reassembled by its own gravity. In this cataclysmic scenario, a massive object plowed into the moon with such force that it broke apart completely. Over time, the fragments, ranging from vast chunks of crust to fine powder, slowly drifted back together, coalescing into the patchwork world we see today. The different terrain types would represent the remnants of the original moon's core, mantle, and crust, all jumbled together in a chaotic but gravitationally stable collage. This shatter and reassemble theory is compelling, but it's not the only one. Another intriguing possibility is that Miranda experienced multiple, less destructive but still massive impacts. Instead of one single world-shattering event, a series of gigantic collisions could have partially disrupted the Moon, each time melting large portions of its interior and triggering massive resurfacing events. The coronae could be the frozen remains of these enormous impact basins, which were later modified by internal upwelling. The debate between a single catastrophic breakup and multiple major impacts continues, and the truth likely holds the key to understanding the early history of the entire Uranian system. Miranda's bizarre surface is a frozen record of a time of incredible violence, a period when moons were not just cratered but torn asunder and remade. It stands as a stark reminder that the processes shaping our solar system are not always gentle, and that some worlds bear the spectacular scars of their tumultuous origins for billions of years. While the dark, narrow rings of Uranus pose one riddle, the forces that sculpt and confine them present another layer of celestial engineering. This brings us to the ninth mystery, the intricate gravitational dance of the shepherd moons and the perplexing phenomenon of incomplete ring arcs. Envision a vast, diffuse stream of icy particles stretching around the planet, naturally tending to spread out and dissipate over time. Now imagine a pair of tiny celestial sheepdogs, one running just inside the stream and the other just outside, using their gravity to nudge any stray particles back into the fold. This is the essential role played by moons like Cordelia and Ophelia, the inner guardians of Uranus's epsilon ring, the planet's brightest and outermost major ring. These shepherds are astonishingly small and faint. Cordelia, the inner moon, is only about 40 kilometers across, while Ophelia, the outer one, is even smaller. They don't clear a path through the ring material, but instead, their gentle but persistent gravitational influence creates a phenomenon known as orbital resonance. As a ring particle orbits, it periodically receives a tiny gravitational tug from one of these moons. If the particle's orbit speeds up and moves slightly outward, Ophelia's gravity tugs it back inward. If it slows and falls inward, Cordelia's gravity gives it a push back outward. This constant, coordinated herding prevents the ring from either collapsing into the planet or diffusing away into space, confining the countless fragments into a sharply defined, narrow band. It's a delicate, ongoing ballet of forces, a testament to how even the smallest moons can exert an outsized influence on their environment. But the strangeness doesn't end with perfectly confined rings. Elsewhere in the Uranian system, and indeed in the ring systems of Neptune as well, astronomers have observed something even more peculiar: ring arcs. These are not complete, unbroken loops of material, but dense, clumped segments like scattered beads on a celestial necklace. Instead of a continuous circle, you have a brilliant, concentrated arc of dust and ice, followed by a long, faint, or even empty stretch before the next bright arc appears. The fundamental question is, why doesn't this material simply spread out evenly under the laws of orbital motion? What invisible barrier or celestial glue is holding these clumps together? The leading theory for the stability of these arcs again involves the subtle magic of shepherd moons, but with an added twist of orbital resonance. The idea is that a single, small moon, orbiting just inside or outside the arc, is in a precise gravitational lockstep with the clumped material. For example, the Moon and the arc particles might be in a 1 to 136 resonance, meaning for every 136 orbits the Moon completes, the arc particles complete 137. This specific, repeating alignment creates stable points in space, known as Lagrange points, where the competing gravitational tugs from the planet and the Moon effectively trap the ring material, preventing it from dispersing. It's as if the shepherd moon is conducting a gravitational symphony, creating pockets of stability where the dust and ice can safely congregate without being pulled apart. The existence of these arcs suggests a system in a state of delicate, transient balance. Some scientists propose they are temporary features, perhaps the remnants of a recently shattered moon that are slowly either coalescing into a new satellite or spreading out to form a full, uniform ring over millions of years. Studying these incomplete circles offers a rare, real-time glimpse into the dynamic and ever-changing processes that continuously shape and reshape the architecture of planetary systems. Delving beneath the planet's tilted spin and frigid interior, we encounter a more subtle but equally profound enigma: the strange and layered composition of its atmosphere. At first glance, the Uranian sky might seem like a simpler version of the hydrogen and helium-dominated envelopes of Jupiter and Saturn. But it's the trace gases, the chemical fingerprints present in only small amounts, that reveal a world of hidden processes and peculiar chemistry. The most famous of these is, of course, methane. This simple molecule, composed of one carbon atom bonded to 4 hydrogen atoms, is the artist behind the planet's signature serene blue-green appearance. But how does a gas create such a distinctive color? The science lies in the interaction between sunlight and the atmospheric gases. Sunlight contains all the colors of the rainbow, and as it enters the atmosphere of Uranus, the hydrogen and helium are largely transparent to these wavelengths. Methane gas, however, is a selective absorber. It has a powerful appetite for the red and orange portions of the spectrum. When sunlight passes through a deep layer of atmosphere rich with methane, these warm colors are filtered out and absorbed, while the cooler blue and green wavelengths are scattered back into space. It's the same basic principle that gives Earth's sky its blue color, but with a different gas acting as the filter. The result is the tranquil, aquamarine visage we observe. The depth of the blue-green color also tells us something important. There must be a substantial amount of methane welling up from below to create such a strong effect, indicating an active, though sluggish, circulation between the lower and upper atmosphere. But if methane solves one visual mystery, the case of a missing gas deepens another. In the upper cloud decks of Uranus, astronomers have found a startling and significant absence: ammonia. This is deeply puzzling because, based on our models of how the solar system formed, Uranus should be rich in nitrogen, and ammonia, a compound of nitrogen and hydrogen, is expected to be a major component of the icy planetesimals that built the ice giants. So, where has all the ammonia gone? It hasn't vanished. The prevailing theory is that it has been effectively hidden from view, sequestered deep beneath the visible cloud tops. The explanation lies in the extreme cold and the unique structure of the Uranian atmosphere. Think of the atmosphere as a giant, multi-layered freezer. At the incredibly low temperatures found in the upper atmosphere of Uranus, ammonia becomes highly soluble in water. Scientists hypothesize that below the visible methane cloud layer, there exists a deeper, much thicker cloud layer composed of water ice and water vapor. In this frigid, high-pressure environment, any ammonia that welled up from the interior would be readily absorbed into the water droplets, creating a solution of ammonium hydroxide, essentially a vast global cloud of freezing household cleaner. This process effectively traps the ammonia, preventing it from rising to levels where our telescopes and spacecraft can detect its spectral signature. This hidden reservoir also acts as a powerful antifreeze, depressing the freezing point of the water-ammonia mixture and allowing it to remain in a slushy, liquid state at much colder temperatures than pure water could. This deeply buried water-ammonia cloud deck is likely a key part of the planet's internal weather machine, and its existence helps explain the bizarre thermal properties and the sluggish heat transport that contributes to the planet's profound cold. The absence of ammonia in the upper atmosphere is therefore not an absence at all, but a clue pointing toward a complex, layered atmospheric chemistry happening entirely out of sight. This brings us to the 11th great puzzle, the paradox of the planet's weather, where a world with a seemingly dead engine manages to whip up some of the fastest winds in the solar system. You might logically assume that a planet as profoundly cold and lacking in internal heat as Uranus would have a sluggish, placid atmosphere, yet the opposite is true. Tracking the movement of distant, faint cloud features has revealed that Uranus is scoured by ferocious zonal winds, jet streams that race parallel to its equator at speeds exceeding 500 miles per hour. To put that into perspective, that's more than twice the wind speed of the most powerful tornadoes ever recorded on Earth. This creates a monumental contradiction. Where is the energy to drive such a violent atmospheric circulation coming from, if not from within the planet itself? The answer appears to lie in a delicate and complex interplay between the feeble sunlight and the planet's extreme seasons. Remember, Uranus has virtually no internal heat to churn its atmosphere from below, so its weather system is almost entirely solar-powered, but in a uniquely skewed way. During the long decades of its solstices, when one pole is pointed directly at the sun, that hemisphere receives a massive, uninterrupted influx of solar energy. This creates a tremendous temperature imbalance between the sunlit pole and the dark, frigid equator. The atmosphere, striving to reach equilibrium, responds by developing these immense jet streams to transport heat from the warm region to the cold one. It's a planetary-scale heat engine, but one that is fundamentally different from Jupiter's or Neptune's, which are stoked from within. On Uranus, the driving force comes entirely from the top down, from the way sunlight is distributed across its tilted face. The planet's rapid rotation a day on Uranus is just over 17 hours long, then takes this thermally driven motion and stretches it, shearing it into the tight, eastward and westward blowing bands that encircle the globe. This leads to another baffling aspect of Uranian weather: its generally bland and featureless appearance, punctuated by sudden, dramatic outbursts. For most of our observational history, Uranus presented itself as a nearly uniform, smooth blue-green marble. The Voyager 2 flyby in the 1980s captured this quiescent state, showing only a handful of faint cloud bands and a handful of small, bright spots. This blandness is a direct result of that low internal heat. Without a strong convective engine bubbling up from below to form towering cloud structures and massive, long-lived storm systems like Jupiter's Great Red Spot, the atmosphere tends to settle into a stratified, hazy calm. The weather is deep, but it is also lethargic and largely hidden beneath a thick, photochemical smog created when sunlight breaks apart methane molecules. Then, without warning, this serene facade shatters. On several occasions, most notably around the planet's equinox in 2007, astronomers using the Hubble Space Telescope and advanced ground-based observatories witnessed the sudden eruption of colossal, brilliant white cloud features. These storms grew to be continent-sized on Earth, becoming some of the brightest features ever seen in the outer solar system. They churned through the atmosphere, evolving over days and weeks before fading away just as mysteriously as they appeared. The leading theory is that these are giant convective storms, similar to monstrous thunderstorms on Earth but on a planetary scale. As seasonal sunlight finally reaches the dark, frozen hemisphere during the equinox, it triggers a sudden and violent instability. Sunlight penetrates the upper haze, warming a deep layer of the atmosphere and causing a massive plume of material, likely methane ice crystals, to erupt buoyantly from the lower clouds, punching through the stagnant upper layers and creating a brilliant, high-altitude cloud cap that we see from Earth. Their fleeting nature suggests that Uranus's atmosphere has a very different way of releasing its pent-up seasonal energy compared to other giants. Not in a constant, churning roar, but in sudden, spectacular, and temporary explosions that briefly illuminate its hidden meteorological fury before the deep freeze sets in once again. This unusual makeup forces us to confront a foundational question about the very beginning of our solar system. How did Uranus end up with such a radically different recipe? The story of its icy composition is a cosmic detective story, leading us back over 4.5 billion years to the swirling protoplanetary disk of gas and dust that surrounded our infant sun. In the classic model of planetary formation, the temperature of this disk decreased with distance from the Sun. Close in, where temperatures were scorching, only metals and silicate rocks could condense into solid grains, leading to the formation of the rocky inner planets. Further out past what's known as the frost line, it was cold enough for volatile compounds like water, ammonia, and methane to freeze into solid ice. Jupiter and Saturn are thought to have formed just beyond this line, allowing them to rapidly accrete massive cores from both rock and ice, which then pulled in enormous envelopes of hydrogen and helium gas, becoming the gas giants we know today. Uranus and Neptune, however, present a fascinating deviation from this pattern. They have the mass of giants but the composition of oversized, icy cores. This suggests they formed in a region where the raw materials were different and the process was less efficient. One compelling theory posits that they did indeed form much closer to the Sun, perhaps near or even between the orbits of Jupiter and Saturn. In this chaotic early environment, their growing cores would have been able to rapidly accumulate a significant amount of the surrounding hydrogen and helium gas. But then, a gravitational upheaval occurred. The immense gravity of the young Jupiter is thought to have destabilized the entire system, scattering smaller protoplanets and debris everywhere. In this grand tack, or nice model scenario, Uranus and Neptune were essentially flung outward, migrating to their current distant orbits. During this violent journey, the majority of their primordial hydrogen and helium envelopes could have been stripped away by the Sun's intense radiation or through gravitational interactions with other bodies, leaving behind their dense, icy cores with only a relatively thin topping of gas. An alternative and perhaps more straightforward hypothesis is that Uranus formed right where it is now, but from a unique and depleted population of planetesimals. In the far reaches of the solar system, the protoplanetary disk was much less dense. Here, the process of core accretion would have been a slow, painstaking affair. It would have taken so long for a planetary core to grow large enough to start pulling in a massive gas envelope that by the time it reached a critical size, most of the primordial hydrogen and helium in its vicinity had already been dispersed by the young Sun's intense solar winds. Uranus, in this view, is a planet that simply ran out of gas literally. It finished its core assembly just a bit too late to become a true gas giant, forever remaining an ice-dominated world, a testament to the timing and resource availability in its particular neighborhood. This fundamental mystery of its origin is directly linked to so many of its other bizarre traits. That proposed impact that knocked it on its side, for instance, becomes more plausible if the planet was migrating through a crowded early solar system, dramatically increasing the chances of a colossal collision. Its lack of internal heat also fits this narrative. If it formed slowly from colder building blocks in the outer fringe, it may have started with less primordial heat to begin with, and the process of migration or the stripping of its outer layers could have further drained its thermal reserves. Understanding whether Uranus is a displaced world or a true native of the outer darkness is therefore key to unlocking its entire history. Each piece of ice in its vast interior is a frozen relic from the solar system's birth, holding clues not just to one planet's past, but to the dynamic and often violent processes that built all the worlds orbiting our Sun. Deepening our probe into the planet's invisible forces, we reach the 13th mystery, the faint, cryptic radio whispers emanating from Uranus. Every planet with a magnetic field sings a song of sorts, a crackle and hum of radio waves generated as charged particles from the solar wind spiral along magnetic field lines. But Uranus doesn't sing a clear, steady note. Its radio emissions are a weak, broken signal, a transmission that stutters and fades in a pattern directly tied to its wildly skewed and wobbling magnetosphere. When the Voyager 2 spacecraft listened in during its flyby, it detected these signals, and they revealed a magnetosphere that isn't just lopsided, but one that behaves more like a blinking strobe light than a steady beacon, turning on and off with the planet's clumsy rotation. The key to this erratic broadcast lies in the unique geometry of the magnetic field. Because the field is so severely tilted and offset from the planet's center, the entire magnetosphere is dragged around in a lopsided wobble as Uranus spins. For parts of its 17-hour day, the magnetic poles align in a way that efficiently funnels charged particles from the solar wind down into the atmosphere, sparking the generation of radio waves. At other times, the configuration is such that this funneling process is disrupted, and the radio emissions essentially switch off. This creates a highly unstable and asymmetric magnetic environment, one that opens and closes to the solar wind in a chaotic rhythm. It's as if the planet has a faulty electrical connection, flickering on and off as its internal dynamo struggles to maintain a consistent presence in the solar system. What makes these faint radio signals so valuable is that they act as a remote diagnostic tool, allowing us to peer into the dynamics of a magnetosphere we cannot directly visit. The specific frequencies and pulsing patterns of the emissions tell scientists about the strength of the magnetic field and the density of the charged particles, primarily electrons, trapped within it. The data suggests that Uranus's radiation belts, the zones where these particles are concentrated, are far more anemic and disorganized than those of Earth or Jupiter. This weakness points to other hidden processes at work. There may be efficient loss mechanisms where particles are rapidly drained away, perhaps by crashing into the extensive ring system or being absorbed by the inner moon. Alternatively, the strange magnetic field geometry might simply be terrible at trapping particles for long periods, allowing them to escape easily back into interplanetary space. These radio whispers, therefore, are not just a curiosity. They are a direct report from the front lines of the interaction between the solar wind and one of the most dysfunctional magnetic fields we have ever encountered. But if you thought the weather on Uranus was merely a matter of high winds and seasonal outbursts, prepare to witness a phenomenon that reveals the true depth of its atmospheric power, the fleeting and mysterious dark spots. While Jupiter's Great Red Spot is a permanent, centuries-old fixture, the dark spots of Uranus are more like phantoms, gigantic, swirling vortex storms that appear without warning, dominate the atmosphere for a few months or years, and then vanish just as mysteriously. The first of these elusive features was spotted by the Hubble Space Telescope in 2006, a sprawling dark vortex large enough to swallow several Earths, accompanied by bright companion clouds of methane ice. Since then, only a handful of others have been detected, making each observation a precious clue to the inner workings of this world. So, what exactly are these colossal, shadowy storms? They are essentially massive anticyclones, high-pressure systems where atmospheric gas is slowly sinking rather than rising. On Earth, high-pressure systems typically bring clear, calm weather. But on Uranus, the dynamics are inverted and amplified on a planetary scale. In the cold, deep atmosphere, these sinking motions may be clearing out the high-altitude methane haze, creating a hole or a well in the upper cloud deck that allows us to peer down into a warmer, darker layer of the atmosphere below. This creates the stark contrast of a dark spot against the brighter blue-green background. The bright, feathery clouds often seen clinging to these spots are believed to be methane ice crystals that form as the air, forced to rise around the edges of the sinking vortex, cools and condenses, much like how water vapor forms clouds over mountain ranges on Earth. These spots are not just surface features, they are windows into the complex vertical structure of the Uranian atmosphere, revealing circulation patterns that reach deep into the planet's hidden interior. The primary reason these dark spots are so much rarer and harder to study than their counterparts on Jupiter or Neptune comes down to two fundamental Uranian traits: its profound lack of internal heat and its general atmospheric blandness. A strong internal heat source, like the one driving Neptune's Great Dark Spot or Jupiter's perpetual storms, provides constant, powerful convection that can punch through the upper atmosphere and sustain long-lived vortices. Uranus, with its feeble internal engine, lacks this consistent driving force. Its storms are instead primarily triggered by seasonal solar heating. When the shifting sunlight during equinox creates massive instabilities, it can spawn these colossal vortices, but without a strong internal furnace to keep them churning, they are far more susceptible to being sheared apart by the planet's fierce zonal winds or simply dissipating as the seasonal energy balance shifts. Furthermore, the thick, photochemical haze that shrouds Uranus often obscures these features from our view, making them visible only during these rare periods of intense atmospheric upheaval when they are powerful enough to clear a path through the smog. Studying these transient dark spots is absolutely critical because they act as natural tracers, revealing the secrets of deep atmospheric circulation that would otherwise remain completely invisible. By tracking their movement and evolution, scientists can directly measure the speed and direction of the immense wind currents that operate far below the visible cloud tops. The behavior of these vortices confirms that the ferocious winds we detect are not just a surface phenomenon, but extend deep into the atmospheric interior, possibly all the way down to the hypothesized slushy mantle. Each dark spot that forms, swirls, and disintegrates provides a fleeting but invaluable snapshot of the global weather machine at work, a machine powered not from within, but from the slow, relentless rolling of a tilted giant through the rays of a distant sun. Far beyond the stately orbits of Miranda, Ariel, and the other large moons, in the deep, dark reaches of the Uranian system, lies a scattered family of cosmic runts and strays. These are the irregular moons, a collection of at least 9 small, dark worlds, some no more than a few kilometers across, tracing wild, looping paths around their giant parent. Unlike the major moons, which circle neatly around Uranus's equator in nearly perfect circles, these irregulars are celestial rebels. Their orbits are profoundly tilted, highly eccentric, and some even travel backwards, moving in a retrograde direction against the planet's own rotation and the orbital flow of everything else. They are the outsiders, and their very presence tells a story of a young solar system that was a far more violent and chaotic shooting gallery than we often imagine. The central puzzle is how these small objects came to be in orbit around Uranus at all. They didn't form alongside the planet from a neat, orderly disk of gas and dust as the major moons likely did. Their inclined and far-flung orbits are the unmistakable signature of capture. At some point in the distant past, these wanderers were independent bodies, freely orbiting the sun, until a celestial tug of war wrested them away from their original paths and forced them into the service of the ice giant. But capture is not a simple process. An object flying past a planet can't just be snared like a fish in a net. The physics of gravity dictates that an object's speed and energy must change significantly for it to settle into a stable orbit. So how did Uranus manage to pull off this gravitational theft? Astronomers have 2 primary suspects for the original home of these captured moons. The first is the asteroid belt between Mars and Jupiter. The second, and perhaps more likely source, is the Kuiper belt, that vast reservoir of icy remnants beyond Neptune. The composition of these moons is a critical clue, but they are so small, dark, and distant that their surfaces are incredibly difficult to analyze. If they are rich in carbonaceous material, they might be refugees from the asteroid belt. If, however, they are primarily water ice and other volatiles, they are almost certainly exiled Kuiper belt objects, primordial chunks of the solar system's building blocks that never coalesced into a larger planet. Their existence around Uranus suggests that the early solar system was not a neatly zoned neighborhood, but a place where objects from vastly different regions could be thrown into the inner planetary system and subsequently captured. But the how of their capture is perhaps the most fascinating part of the mystery. For gravity to successfully capture a passing object, something must act as a brake to shed the object's excess orbital energy. One compelling theory involves gas drag. In the very early solar system, Uranus was still surrounded by a thick, extended envelope of leftover hydrogen and helium from its formation. A small object passing through this diffuse gas would have experienced friction, slowing it down just enough for the planet's gravity to grab hold and prevent its escape. Another elegant mechanism is a gravitational interaction involving three bodies. In this scenario, an object would approach Uranus as part of a binary pair, two small worlds orbiting each other. As this binary duo swung past the giant planet, its gravity could tear the pair apart, flinging one member away at high speed while the other lost enough momentum to be captured into orbit. It's a cosmic robbery where the gravitational energy of one object is used to pay for the capture of its partner. The orbits of these irregular moons are not static. They are a dynamic, ever-changing record of billions of years of gravitational nudges. Their paths are influenced not only by Uranus but also by the persistent, subtle pull of the Sun and the other giant planets, particularly Jupiter and Saturn. Over eons, these external tugs can cause the orbits to slowly evolve, changing their tilt and eccentricity in a complex dance known as the Kozai mechanism. Studying these intricate orbital pathways is like reading a history book written in gravity. The specific inclinations and directions of these moons can tell us about the conditions in the early Uranian system and even hint at whether Uranus itself may have migrated from a different original position. Each irregular moon is a captured relic, a time capsule from the solar system's most turbulent era, and by mapping their chaotic paths, we are charting the gravitational storms that shaped our entire celestial neighborhood. And so we arrive at a puzzle hidden within the very gas that gives Uranus its beautiful color, the 16th mystery, the curious case of the missing methane. We know methane is there. Its profound ability to absorb red light is what paints the planet in those stunning shades of aquamarine and cyan. But when scientists measure the abundance of this gas in the upper atmosphere, they find it is significantly depleted compared to what standard models predict. It's as if the planet's primary artist is running out of paint, and the question is, where is it all going? The answer seems to lie in a dramatic, planet-wide meteorological cycle, one that involves methane condensing, falling as snow, and being trapped in a deep freeze far below our line of sight. This begins with the unbelievable cold in the upper atmosphere. Remember, Uranus holds the record for the coldest planetary atmosphere in our solar system, with temperatures plunging to a bone-chilling -224 degrees Celsius. At these extreme lows, the conditions are perfect for a phenomenon that is almost sci-fi in nature, methane snow. Just as water vapor in Earth's atmosphere condenses and falls as rain or snow, methane on Uranus can undergo a similar phase change. High in the stratosphere, where temperatures are most severe, methane gas doesn't just form clouds. It can condense directly into ice crystals and begin a slow, perpetual descent toward the warmer layers below. This process effectively acts like a cosmic vacuum cleaner, continually scrubbing methane from the upper atmosphere and depositing it at lower altitudes. Imagine a world where snowstorms aren't made of water, but of frozen natural gas, silently falling for decades on end, and you begin to grasp the surreal weather dynamics at play. But the journey of this methane doesn't necessarily stop there. As the frozen crystals sink, they enter a deeper, hotter, and higher pressure region of the atmosphere. Here, they likely sublimate, turning directly back into gas, only to be caught in vast, slow-moving circulation patterns that might carry them back up to the cold upper layers to condense and fall once more. This creates a closed-loop, vertical conveyor belt for methane, constantly cycling it between gas and ice, and effectively hiding a substantial portion of the planet's methane inventory in a deep, unobservable weather layer. This hidden reservoir has a direct impact on the planet's energy balance. Because methane is a powerful greenhouse gas, its distribution controls how heat is trapped and transported within the atmosphere. By sequestering so much methane deep inside, Uranus may be further inhibiting its own ability to retain and distribute the meager solar energy it receives, contributing directly to its status as the solar system's deep freeze and its profoundly sluggish atmospheric circulation. The uneven distribution we see from afar is therefore not a static condition, but a snapshot of a dynamic, global process of condensation and uplift that helps maintain the planet's serene yet frigid facade. Now, just when you thought this world couldn't possibly offer any more peculiarities, we encounter a ghostly light show emanating from its upper atmosphere, the 17th mystery, the faint ultraviolet glow known as electroglow. Imagine the upper skies of Uranus, far above the methane snow and the dark spots, where the atmosphere thins out into a tenuous veil of hydrogen gas. Here, the planet shimmers with an invisible to our eyes aurora of ultraviolet light, a soft, pervasive luminescence that blankets the entire sunlit hemisphere. This isn't the concentrated, dazzling aurora we see at Earth's poles, but a more diffuse global phenomenon, as if the planet itself is humming with a feeble, energetic tune. The basic physics of electroglow are understood. High-energy electrons colliding with hydrogen molecules in the upper atmosphere excite those molecules, causing them to vibrate with extra energy. When they calm down and return to their normal state, they release that excess energy in the form of ultraviolet photons, creating the glow. This process happens to some extent in the atmospheres of all the gas and ice giants. The profound puzzle with Uranus is the sheer intensity of its electroglow. For a planet so distant, so cold, and with such a weak internal heat source, the phenomenon is unexpectedly bright. It shines with a vigor that rivals the electroglow of much larger and more energetic worlds like Jupiter and Saturn. This creates a fundamental paradox. Where is the immense power coming from to excite so many electrons and generate such a pronounced glow in this otherwise lethargic world? The leading suspect is the Sun, but with a unique Uranian twist. Because the planet's rotational axis is tipped on its side, its poles experience decades of continuous sunlight during their respective summers. This means that for long periods, the upper atmosphere over the sunlit pole is being bombarded by solar ultraviolet radiation and the charged particles of the solar wind without any daily break. This relentless, focused input of energy from the sun might be supercharging the upper atmosphere, creating a dense population of hot, energetic electrons that then collide with the hydrogen gas to produce the glow. It's a scenario where the planet's extreme tilt acts as a giant lens, concentrating solar energy onto one polar region in a way that no other planet experiences, thereby amplifying a process that is usually more uniform across other worlds. Another compelling theory points to the planet's chaotic and wobbling magnetic field. As this lopsided magnetosphere interacts with the solar wind, it could be creating complex electrical currents and accelerating electrons downward into the atmosphere, providing an additional non-solar power source for the excitation. The unique geometry of the Uranian system seems to be turning its entire sunlit face into a giant, efficient engine for producing this eerie ultraviolet light. Studying this faint glow is far more than just investigating a curious atmospheric quirk. It serves as a critical remote sensing tool. By analyzing the specific wavelengths and intensity of the electroglow, scientists can indirectly measure the temperature, density, and composition of Uranus's upper atmosphere, a region that is incredibly difficult to observe by any other means. The strength of the glow tells us about the population of energetic electrons, which in turn reveals how much energy is being deposited from above. This data helps us build a better model of the planet's overall energy budget, that crucial balance between the feeble sunlight it receives, its missing internal heat, and the powerful winds that race through its depths. The surprising brightness of Uranus's electroglow is therefore a vital piece of evidence in the larger puzzle, hinting that there are powerful, high-altitude energy processes at work that we are only beginning to comprehend, processes that help define the strange and complex personality of this tilted ice giant. Peering even closer at those shadowy loops encircling the planet, we encounter a mystery that lies in the very fabric of the rings themselves, the strange and varied nature of the individual ring particles. These aren't uniform little spheres of brilliant ice. Instead, each ring is a chaotic highway of countless fragments, each one a tiny world with its own story. The first and most obvious question is, why are they all so incredibly dark? The leading explanation takes us into a realm of intense radiation and complex chemistry. Out in the space around Uranus, the particles are constantly bombarded by high-energy radiation from the solar wind and trapped within the planet's own magnetosphere. This radiation acts like a cosmic sandblaster, but its effect is chemical. It breaks apart the simple water ice and any organic compounds, reassembling them into a complex, dark, carbon-rich gunk known as tholins. Think of it as a kind of super soot, a substance that forms when simple ices are irradiated over millions of years. This process effectively gives every ring particle a dark, non-reflective coating, rendering the entire system profoundly difficult to see except when they are backlit or blocking the light of a distant star. This explains why the rings are so faint compared to Saturn's. They aren't made of clean, fresh ice, but are instead coated in an ancient, radiation-darkened layer that absorbs most of the sunlight that hits it. But the darkness is only part of the puzzle. The size of these particles reveals an even more complex history. Within a single ring, the particle population isn't uniform. It's a diverse mix ranging from microscopic dust grains, finer than powdered sugar, all the way up to sizable boulders several meters across. This wide distribution is a crucial clue, and it points directly to a violent and dynamic environment. If the rings were simply leftover material from the planet's formation that had never been disturbed, you might expect a more homogeneous mix. Instead, this jumble of sizes strongly suggests a history of relentless collisions and grinding erosion. The larger boulders are likely the original fragments, the shattered remnants of a small moon or several moons that were torn apart by a massive impact or ripped apart by Uranus's gravity. The finer dust is the product of countless subsequent, smaller collisions between these larger fragments over billions of years, a continuous process of grinding down the rubble into ever smaller pieces. This collisional cascade creates a delicate balance between destruction and preservation. The constant grinding would tend to spread the rings out and dissipate them over time, yet the gravitational influence of the shepherd moons works to confine them. This creates a system in a state of equilibrium where the rings are neither rapidly disappearing nor staying perfectly pristine. The size distribution we observe today is essentially a snapshot of this ongoing process. Furthermore, the variations in particle size and density from one ring to another tell a more nuanced story. The bright epsilon ring, for instance, is composed of a much narrower range of particle sizes and contains fewer fine dust grains compared to the inner, more diffuse rings. This suggests that the epsilon ring's shepherd moons are not only confining its orbit, but are also potentially acting as gravitational filters, either ejecting the smallest dust or allowing it to be lost more easily, leaving behind a cleaner population of larger golf ball to boulder-sized chunks. In contrast, the inner rings appear dustier and more diffuse, hinting at either a more recent disruption or a less effective confining mechanism, allowing a greater abundance of fine material to persist. The properties of these countless individual particles, from their sooty surfaces to their varied sizes, are therefore a direct record of the forces that have shaped the Uranian system for eons, a history of catastrophic breakups, slow erosion, and the subtle, shepherding gravity of tiny moons. Moving from the planet's faint electroglow to the solid ground of its satellites, we arrive at a mystery written across the very faces of these moons themselves, the profound and puzzling asymmetry between their leading and trailing hemispheres. Most of the major moons in our solar system present a certain uniformity. Their surfaces are generally ancient and battered, or they are globally young and smooth. But the major moons of Uranus, particularly Ariel and Miranda, display a startling split personality. One side of the moon is often an ancient, dark, and heavily cratered landscape, a fossil record of billions of years of impact. The other side, in stark contrast, can be bright, smooth, and crisscrossed by vast networks of valleys and grooves, showcasing clear evidence of geologically recent resurfacing. This isn't a gentle gradient, it's a dramatic hemispheric divide, as if each moon has two entirely different geological histories stitched together into one world. The key to this puzzle lies in the complex interplay of two powerful forces, tidal heating and orbital resonances. Tidal heating is the frictional warmth generated inside a moon as it is constantly stretched and squeezed by the gravitational pull of its parent planet. On a moon in a perfectly circular orbit, this effect is minimal. But if a moon's orbit is even slightly eccentric, taking it closer and then further from Uranus, the strength of the planet's gravitational pull changes throughout its orbit, creating a rhythmic, internal flexing that generates immense heat. This is the same process that powers the volcanic fury of Jupiter's moon Io and keeps the subsurface ocean of Europa liquid. For the Uranian moons, this internal heat could have been sufficient at times in the past to partially melt their icy interiors, turning them into slushy worlds with a liquid or malleable layer beneath a brittle crust. Now imagine one of these warm, pliable moons orbiting Uranus. As it moves, one hemisphere constantly leads the way, plowing through the space ahead, while the opposite hemisphere trails behind. This simple motion has profound consequences. Geological evidence from Ariel, in particular, suggests that the most intense resurfacing activity, where vast plains of fresh, smooth ice welled up from below, occurred predominantly on its trailing hemisphere. The mechanism likely worked like this. The internal tidal heat created pressure in the moon's subsurface ocean or slushy mantle. This pressurized, warm material sought the path of least resistance to escape. The trailing hemisphere being the geologically relaxed side as the moon moved away from the peak of the tidal bulge, may have offered a thinner or more fractured crust. Think of it as a zit that always pops on the same side of your face. The internal pressure finds the weakest spot in the outer layer. This allowed floods of viscous water ammonia, lava, to erupt onto the surface, covering the old, cratered terrain with bright, new ice and carving the spectacular, deep canyon networks we see today. The leading hemisphere, meanwhile, remained frozen solid, its ancient, dark surface preserved as a testament to its violent early history. But what could have provided the initial push to make these moons' orbits eccentric enough for such dramatic heating in the first place? This is where the second piece of the puzzle, past orbital resonances, comes into play. An orbital resonance occurs when two moons' orbital periods line up in a simple ratio, like one moon completing two orbits for every one orbit of another. When this happens, their gravitational tugs on each other add up over time, reinforcing their effects rather than cancelling out. This repeated, synchronized pulling can pump energy into the moon's orbits, making them more eccentric and driving the very tidal flexing that generates internal heat. Many planetary scientists now believe that the Uranian moon system was not always in its current, quiet configuration. In the distant past, the orbits of moons like Ariel, Umbriel, and Titania may have passed through a series of powerful resonances with each other. For a period of perhaps hundreds of millions of years, this gravitational symphony would have churned the system, dramatically heating the interiors of the inner moons and triggering global-scale geological upheavals. This theory elegantly explains not just the activity on Ariel and Miranda, but also the stark contrasts between the moons themselves. Umbriel, for instance, is uniformly dark and heavily cratered, showing almost no signs of this kind of resurfacing. This suggests it may never have been caught in a strong resonance, or that its internal composition was different. Perhaps it lacked the antifreeze like ammonia that would have allowed its interior to remain mobile and erupt onto the surface. Miranda, the most fractured of all, might represent an extreme case where tidal heating was so intense it nearly tore the moon apart, leading to its bizarre patchwork terrain of ancient crust and young, resurfaced coronae. The resonances would not have lasted forever, as the moons gradually migrated outward due to tidal interactions with Uranus. They would have eventually fallen out of these precise alignments. The gravitational pumping stopped, the tidal heating ceased, and the moons froze solid, locking in the dramatic asymmetry of their surfaces for the rest of time. The hauntingly different faces of these moons are therefore a frozen clock, capturing the moment a celestial dance of gravity fell out of sync, leaving one hemisphere to tell a story of ancient violence and the other a story of a brief, fiery youth. Looming far above the planet's methane snowstorms and faint dark spots, in the most tenuous reaches of its atmosphere, lies a ghostly and immense halo of gas, a feature so ethereal we can only detect it through its faint absorption of ultraviolet light. This is the hydrogen corona of Uranus, a vast, extended cloud of individual hydrogen atoms that stretches tens of thousands of kilometers beyond what we would normally consider the planet's atmospheric boundary. Think of it as the planet's final, fading breath, a diaphanous shroud that envelops the entire world, reaching out into the void of interplanetary space. While all the giant planets possess such a feature, the Uranian corona stands out for its surprising extent and its puzzling behavior, presenting a unique set of challenges to our understanding of atmospheric escape and the complex interplay between a planet, its magnetic field, and the solar wind. The fundamental process that creates this corona is known as Jean's escape, a gentle but relentless trickle of particles into space. High in the upper atmosphere, where the air is incredibly thin, individual hydrogen atoms are constantly zipping around at tremendous speeds, their motion dictated by the local temperature. Occasionally, an atom near the top of the atmosphere will receive just enough energy from a random collision or from absorbing solar radiation to achieve escape velocity, the speed needed to break free from the planet's gravitational grip entirely. Once free, these atoms form the diffuse corona, a cloud that is bound to the planet but not part of its dense, lower atmosphere. It's a slow, constant bleeding of the lightest element into space, a process that has likely been ongoing since the planet's formation. However, Jean's escape alone doesn't seem sufficient to explain the observed size and density of Uranus's hydrogen envelope. This leads scientists to suspect that other, more powerful mechanisms are at work, potentially supercharging this atmospheric leak. One compelling suspect is a process called charge exchange, a subtle atomic dance that occurs where the planet's environment meets the flood of particles from the sun. The solar wind is a relentless stream of charged particles, primarily protons and electrons, blowing outward from the sun. When a fast-moving solar wind proton approaches the Uranian system, it can encounter a slow-moving hydrogen atom from the planet's extended corona. In a moment of interaction, the proton can steal an electron from the neutral hydrogen atom. In an instant, the identities swap. The fast proton becomes a fast, neutral hydrogen atom, while the formerly slow hydrogen atom becomes a slow, charged proton. This newly created neutral atom, now imbued with the high speed of the solar wind, is completely unaffected by magnetic fields and can fly off in any direction, effectively becoming a new member of the extended corona. Meanwhile, the new, slow proton gets picked up by the solar wind or the planet's magnetic field and is swept away. This process doesn't just slowly leak atmosphere, it actively injects energetic hydrogen into the far reaches of the corona, potentially explaining how it can maintain such a vast and tenuous structure. The profound mystery, however, is that the observed density and structure of this hydrogen shroud don't perfectly match our theoretical models. Data from the Voyager 2 flyby and subsequent Earth-based observations suggest the corona is both more extensive and behaves more erratically than predicted. A key reason for this discrepancy almost certainly lies in the planet's bizarre and wobbly magnetic field. On a world like Earth, the magnetic field acts as a mostly reliable shield, deflecting the solar wind and carving out a relatively stable, protected space, the magnetosphere within which the atmosphere resides. Uranus's magnetosphere is nothing like this. Its severe tilt and off-center location mean it is constantly shifting, wobbling, and potentially even rolling relative to the solar wind. This creates a highly dynamic and asymmetric interface where the solar wind can more directly impact and interact with the upper atmosphere at certain points in the planet's rotation. This chaotic interaction could dramatically enhance the loss of hydrogen through processes like charge exchange, or it could alternatively create temporary pockets where the corona is denser or more extended in one direction than another. The corona, therefore, isn't a static, symmetrical bubble. It's a breathing, pulsing entity that changes its shape and density in rhythm with the planet's clumsy magnetic dance. Understanding the precise nature of this hydrogen loss is critical because it speaks to the planet's long-term evolution and its fundamental composition. Hydrogen is the lightest and most easily lost element, and over billions of years, even a slow leak can significantly alter the chemical makeup of a world's atmosphere. By measuring the current rate of escape from the corona, scientists can work backwards to estimate how much hydrogen Uranus has lost over its lifetime and how this has affected the relative abundance of heavier gases like helium and methane that we see today. Furthermore, the behavior of the Uranian corona serves as a crucial comparative data point. It helps us understand atmospheric escape not just as a generic process, but as a phenomenon deeply sculpted by a planet's unique gravitational field, magnetic personality, and its position in the solar system. This faint, ultraviolet halo, barely more than a wisp of gas against the blackness of space, is therefore a dynamic and active frontier, a laboratory for studying how a world gradually sheds its own atmosphere under the influence of a distant star and its own internal, broken compass. If you thought the rings of Uranus were the only structures gathering dust, think again, because the 21st mystery reveals an environment that is almost unnervingly clean. While the planet is encircled by its dark, narrow rings, the space between and around them is strikingly devoid of the fine, dusty material that fills the orbital neighborhoods of other ringed giants. Saturn, for example, is enveloped in a vast, hazy disk of microscopic particles, and even Jupiter's faint rings are embedded within a cloud of dust. But around Uranus, this interplanetary grit is conspicuously scarce, creating a puzzle of celestial housekeeping on a planetary scale. Where has all the dust gone, and what powerful janitorial force is keeping the Uranian system so impeccably tidy? The source of this dust is not in question. It is a constant byproduct of the relentless chaos of the solar system. Micrometeoroids, tiny fragments no larger than grains of sand, are perpetually slamming into the surfaces of the moons and ring particles at incredible speeds. These hypervelocity impacts vaporize a small amount of material and blast countless even smaller dust grains into space, a process that should, over time, create a permanent, diffuse cloud of fine powder orbiting the planet. The fact that we don't see this cloud around Uranus means something is actively and efficiently removing the dust almost as fast as it is produced. The leading suspects in this cosmic cleanup are a combination of gravitational sweeping, electromagnetic expulsion, and perhaps even the subtle but persistent pressure of sunlight itself. One of the most effective dust removal mechanisms is likely the family of moons themselves. Uranus's numerous satellites, from the large major moons down to the tiny, unseen moonlets that may orbit within the ring system, act as gravitational vacuum cleaners. As a tiny dust grain enters the gravitational influence of a moon, it can be pulled out of its orbit and drawn down to crash onto the moon's surface. This process is particularly efficient for the inner moons, which sweep through the orbital paths where dust would naturally accumulate. Furthermore, many of these moons are co-orbital, meaning they share similar orbits with the ring arcs and with each other. Their repeated gravitational tugs can create chaotic zones, perturbing the delicate paths of dust grains and either sending them cascading down into the planet's upper atmosphere or ejecting them out of the system entirely. It's a slow but relentless cleansing where the moons act as celestial sponges, soaking up the finely powdered evidence of countless small collisions. But gravity alone may not be enough to explain the thoroughness of the cleanup. This is where Uranus's bizarre and lopsided magnetic field enters the story, adding a powerful and unique element to the mystery. Most of the fine dust in a planetary system becomes electrically charged, either by absorbing ultraviolet light from the sun or through collisions with the charged particles of the solar wind. Once a dust grain carries a net electric charge, it becomes susceptible to electromagnetic forces. Within Uranus's chaotic and wobbling magnetosphere, these charged dust particles can experience strong Lorentz forces, the same forces that bend the paths of electrons in a particle accelerator. The wildly changing magnetic field could thus act like a giant, erratic slingshot, grabbing hold of charged dust grains and flinging them on new trajectories. Some might be accelerated inward to be lost in the planet's atmosphere, while others could be given enough of a kick to achieve escape velocity, banishing them to solar orbit forever. This electromagnetic scavenging would be far more efficient and rapid than gravitational sweeping alone, providing a potential explanation for the exceptional cleanliness of the Uranian environment. A third, more subtle player in this drama is the faint but persistent push of solar radiation pressure. Sunlight, while not possessing mass, does carry momentum, and when photons strike a tiny dust grain, they give it a minute push. For larger objects, this effect is negligible, but for micrometer-sized dust particles, the pressure from sunlight can be a significant force over time. This gentle, continuous nudge can slowly alter a dust grain's orbit, either causing it to spiral inward or outward. In a stable system, this might just redistribute the dust, but in the dynamically complex environment of Uranus, with its moons and magnetic field actively removing particles, solar radiation pressure could be the final straw that pushes a wavering grain over the edge, ensuring it is eventually captured or ejected rather than remaining in a stable orbit. The remarkable scarcity of dust around Uranus is therefore not the result of a single, simple process, but likely the product of a perfect storm of cleaning mechanisms: gravitational moons acting as sponges, a chaotic magnetic field acting as a slingshot, and solar light acting as a gentle but persistent broom, all working in concert to maintain the ice giant's unusually pristine orbital space. Buried deep within the Uranian atmosphere lies a meteorological paradox that turns our everyday experience with temperature completely upside down. This is the planet's thermal inversion layer, a region where, contrary to all intuition, the air gets warmer the higher you go. On Earth, we're used to the opposite. When you climb a mountain, the temperature drops. This normal pattern, where temperature decreases with altitude, is called the troposphere, and it's driven by the fact that the ground absorbs sunlight and heats the air closest to it. But high above the visible cloud decks of Uranus, there exists a boundary where this logic flips. Here, in a stratum known as the stratosphere, the thermometer climbs steadily as you ascend into what should be the cold void of space. This isn't a unique feature. Earth has a stratospheric temperature inversion, too, but the forces that create it on Uranus and its resulting intensity are profoundly alien, born from a delicate and complex interplay of solar energy and exotic atmospheric chemistry. The engine behind this inverted heating is a process called solar energy absorption, but the fuel is a cocktail of gases unlike anything in our own skies. On Earth, our stratosphere warms because of a layer of ozone. a special molecule made of 3 oxygen atoms that is exceptionally efficient at absorbing the sun's harmful ultraviolet radiation. Uranus, however, has virtually no ozone. Instead, the heavy lifting is done by 2 primary constituents, methane and its chemical byproducts. The process begins when fierce ultraviolet light from the sun slams into methane molecules high in the Uranian atmosphere. This high-energy radiation doesn't just warm the gas, it has enough power to break the molecular bonds, shattering methane into smaller fragments like methylene and methyl radicals, and freeing individual hydrogen atoms. These fragments are highly reactive, and they quickly engage in a complex dance of chemical recombination, forming more complex hydrocarbons like ethane and acetylene. It is this entire family of hydrocarbon gases, created and sustained by the relentless breakdown of methane, that acts as a powerful sponge for solar radiation. They absorb the sun's ultraviolet energy, convert it directly into heat, and in doing so, they supercharge a localized layer of the atmosphere, creating the thermal inversion. What makes Uranus's inversion layer so distinctive and powerful, however, is the combination of its atmospheric composition and its extreme seasonal cycle. The planet's atmosphere is dominated by hydrogen and helium, which are largely transparent to this kind of heating. This means there is very little other gas to dilute or distribute the intense, concentrated heat generated by the hydrocarbon layer. All the solar energy being absorbed gets dumped into a relatively narrow band of the sky, leading to a very sharp and pronounced temperature gradient. Furthermore, the planet's 98-degree tilt subjects its poles to 42 years of continuous sunlight. During this long polar summer, the high-altitude hydrocarbon haze over the sunlit pole is bombarded by ultraviolet radiation without a single moment of darkness. This relentless, focused solar input can make the thermal inversion over the summer pole significantly stronger and warmer than the same layer over the equator, creating a bizarre scenario where the upper atmosphere at the pole might be hotter than the equatorial stratosphere, a pattern completely reversed from what we see on other worlds. Comparing this to Earth's own inversion reveals just how peculiar Uranus truly is. Our ozone layer is a stable, global blanket that provides a relatively uniform shield. The Uranian hydrocarbon layer, by contrast, is a dynamic and ever-changing chemical factory. The hydrocarbons produced are not permanent. They eventually condense into tiny, icy haze particles that begin to slowly sink out of the stratosphere, falling down toward the colder, lower layers in that perpetual methane snow we discussed earlier. This means the Uranian stratosphere is in a constant state of flux, with its primary heating agents being continuously produced, consumed, and lost. The properties of this layer are therefore not static. They change with the seasons, with the 11-year cycle of the sun's ultraviolet output, and with the complex circulation patterns that transport these gases from the pole drenched in midnight sun to the pole locked in deep freeze. This makes the thermal inversion of Uranus not just a curious atmospheric layer, but a sensitive barometer of the planet's global climate, a region where chemistry, radiation, and orbital mechanics combine to create a thermal structure that is uniquely fitted to this rolled-over ice giant. Now we venture into one of the most thrilling mysteries of the outer solar system: the possibility of hidden, liquid water oceans lurking beneath the frozen crusts of Uranus's moons, and perhaps even within the planet itself. In this distant, frigid realm where sunlight is a mere 9/100th of its strength at Earth, the very idea of liquid water seems preposterous. Yet, the fundamental ingredients for life as we know it, water, energy, and organic chemistry, might just be present in these dark, silent worlds, transforming them from inert balls of ice into potential havens for alien biology. Let's first consider the largest moons, Titania and Oberon. Each is over 1,500 kilometers in diameter, massive enough to have retained significant heat from their violent formation billions of years ago. But the primary heat source that could maintain a subsurface ocean today is likely radioactive decay within their rocky cores. Deep inside these moons, elements like uranium, thorium, and potassium release heat as they slowly break down over eons. This gentle, persistent radioactive warmth acts like a cosmic space heater, but on its own, it might not be sufficient to keep a vast ocean from freezing solid. This is where a remarkable natural antifreeze comes into play: ammonia. Scientists hypothesize that the original building blocks of these moons were rich in ammonia, and when mixed with water, it creates a brine that can remain liquid at temperatures as low as -100 degrees Celsius. A deep layer of this ammonia-rich water, trapped between a frozen surface crust and a solid rocky core, could potentially persist for the entire age of the solar system, creating a dark, pressurized abyss utterly isolated from the universe above. The case for an ocean becomes even more compelling for the more dynamic moon, Ariel. Its strikingly young and smooth surface, crisscrossed by enormous, fluid-filled canyons, provides the most visible evidence of a geologically active past. Those smooth plains look exactly like regions where a slushy water-ammonia mixture erupted from the interior and flooded the landscape before freezing. This kind of cryovolcanism strongly suggests that Ariel had, and may still have, a warm, mobile interior. The heat needed to power this activity likely came from a different source than simple radioactivity, tidal heating. In the past, Ariel's orbit may have been more eccentric, tracing a slight oval rather than a perfect circle. As it moved closer to and further from Uranus during each orbit, the planet's immense gravity would have stretched and squeezed the moon's interior, generating intense internal friction. This process can produce far more heat than radioactivity alone, potentially creating a global subsurface ocean that periodically broke through the crust to resurface vast areas. While Ariel's orbit is more circular today, damping this heating, its ocean could still be liquid, its freezing slowed to a crawl by the ammonia antifreeze, a relic of a more violent youth. But the crown jewel of potential habitability in this system might be the most fractured and bizarre moon of all, Miranda. Its jumbled, chaotic terrain suggests a history of such extreme internal turmoil that it could have hosted, and may still host, transient pockets of liquid water. The colossal upwellings that created its giant coronae would have generated immense heat, perhaps enough to melt vast regions of its interior for millions of years at a time. While any ocean on such a small moon would likely be unstable and intermittent, freezing and thawing with its geological cycles, it creates the possibility of diverse chemical environments. Where there is liquid water, energy, and a mix of complex chemicals like the organic tholins we suspect exist on these moons, the basic conditions for life, at least as we understand it, are met. These would not be sun-drenched seas, but dark, profound abysses, potentially heated from below by hydrothermal vents, not unlike those on Earth's ocean floor that support vibrant ecosystems completely independent of sunlight. The most radical and far-reaching hypothesis, however, involves the giant planet itself. Could Uranus harbor a subsurface ocean? While we typically envision its interior as a vast, superheated slush, some planetary scientists speculate that a distinct liquid water layer might exist within the planet's deep atmosphere. At the immense pressures found thousands of kilometers below the cloud tops, the conditions could allow for a raining out of water and other compounds, creating a separate global layer of superheated, electrically conductive fluid. This would not be an ocean you could swim in, but a bizarre, high-pressure plasma-like state of matter where the very concept of liquid and gas blurs. The primary evidence for this comes from the planet's lopsided magnetic field. The dynamo generating that field is almost certainly happening within a conductive fluid, and while the superheated water ice mantle is the leading candidate, a more defined liquid water ammonia layer could also fit the data. It's a speculative idea, but if true, it would mean the most abundant form of water in the Uranian system is not on the moons, but hidden deep within the churning, pressurized heart of the ice giant. Evaluating the habitability of these potential oceans forces us to confront the nature of life itself. Any organisms in these lightless depths would need an energy source completely divorced from photosynthesis. On Earth, chemosynthetic bacteria around deep sea vents derive their energy from chemical reactions, such as the conversion of hydrogen sulfide into sulfate. Similar processes could be at work in a Uranian moon's ocean, where water reacting with the rocky seafloor or the breakdown of radioactive elements could provide the chemical energy to power a simple microbial food web. The greatest challenge would be the transfer of nutrients. Without global ocean currents, any life would be confined to isolated oases around hydrothermal vents. Yet, the mere possibility that such environments could exist around a planet once thought to be a stagnant, frozen billiard ball completely transforms our perspective. The Uranian system is no longer just a collection of geological curiosities. It is a potential habitat, a distant outpost where the fundamental spark of life might have found a way to ignite and endure in perpetual darkness. The data we have discussed so far, from the chaotic magnetic field to the fleeting dark storms, largely comes from a single, fleeting encounter, the Voyager 2 flyby in 1986. That mission gave us our first and only close-up look at the ice giant, a revolutionary snapshot that completely reshaped our understanding. But a snapshot is precisely what it was: a few brief hours in the life of a world whose seasons last for decades. Just as you cannot understand a person's entire life from a single photograph, we cannot grasp the full dynamic nature of Uranus from a single flyby. This brings us to our 24th great mystery. How has Uranus changed in the nearly 40 years since Voyager's visit, and what profound transformations have we missed? Our post-Voyager view of the planet has been like trying to watch a feature-length film through a keyhole, glimpsing only brief, blurry scenes. For decades, our best telescopes could barely make out any features on that distant blue-green disk. It was only with the launch of the Hubble Space Telescope and the advent of powerful ground-based observatories equipped with adaptive optics that we began to see signs of a world in flux. The most dramatic shift occurred around the planet's equinox in 2007. For the first time since Voyager flew by during the southern summer solstice, the sun was shining directly over the equator, bathing both hemispheres in equal light. And with this seasonal shift, the placid Uranus that Voyager saw erupted into life. Hubble and other telescopes began detecting enormous, bright cloud systems, colossal storms that roiled the atmosphere and shone with an intensity never before seen. These weren't the faint smudges of the 80s, these were continent-sized convective towers, powerful evidence that the planet's weather is not bland, but is instead a system of long dormancy punctuated by violent, seasonal outbursts. The changes go far deeper than just a few temporary storms. The entire thermal structure of the atmosphere appears to be transforming. Recent observations using radio telescopes have probed the planet's deep atmosphere beneath the visible cloud decks, and they reveal a startling development. The South Pole, which endured a 40-year-long winter after Voyager departed, is now significantly warmer than the equator, while the North Pole, moving into its own long winter, is cooling dramatically. This confirms that Uranus undergoes radical climatic shifts, but the data also contains surprises. The atmosphere isn't behaving exactly as our models predicted. The heat isn't being distributed as efficiently as we assumed, leading to even more extreme temperature contrasts than anticipated. Furthermore, the intricate ring system we discovered by accident has also been changing. The rings are slowly precessing, their orbits wobbling over time, and some of the fainter, dusty rings seem to have shifted in brightness and structure, hinting at recent collisions or the gravitational influence of unseen moonlets. Every new observation we make from Earth raises as many questions as it answers, highlighting just how dynamic this seemingly serene world truly is. This immense gap in our knowledge points to a single, undeniable conclusion. The greatest mysteries of Uranus will remain locked away until we send another spacecraft, this time one designed to stay. A flyby like Voyager's was a magnificent first step, but it was fundamentally limited. It could only measure the magnetic field along one narrow path, leaving the global structure of that lopsided magnetosphere largely a mystery. It could only observe a handful of moons in any detail, and it saw Miranda, Ariel, and the others only as they appeared on a single day billions of years ago. We have no idea how their surfaces may have been altered by ongoing geological processes or recent impacts. Most critically, a flyby provides no understanding of seasonal change. We need an orbiter, a mission that can circle Uranus for years, watching as its atmosphere churns through its slow-motion seasons, mapping its magnetic field from every angle, and repeatedly visiting its captivating moons to search for signs of those hidden oceans. The scientific community has recognized this need, and concepts for a flagship Uranus orbiter and probe mission are now at the top of the priority list for planetary science. Imagine a sophisticated spacecraft arriving at Uranus after a decade-long journey, releasing a sturdy probe that plunges into the atmosphere. As it descends, it would directly measure the composition of the hidden layers, finally telling us the true abundance of water, ammonia, and hydrogen sulfide, and solving the mystery of the planet's missing internal heat. The orbiter itself would then spend years weaving through the system, using its suite of instruments to map the surface of every major moon in unprecedented detail, searching for fresh ice deposits that would point to recent cryovolcanic activity. It would precisely track the shepherd moons to understand their intricate dance with the rings, and it would constantly monitor the chaotic wobble of the magnetic field, finally revealing the secrets of the dynamo deep within the planet's slushy interior. Returning to Uranus is no longer just a scientific desire, it is a necessity for completing our understanding of the solar system. The ice giants Uranus and Neptune represent a whole class of planets that is the most common in our galaxy. By ignoring them, we are ignoring the most typical planetary architecture in the cosmos. A mission to Uranus is therefore a mission to understand the most common planets in the universe, to learn the final chapter in the story of our own solar system's formation, and to uncover whether small, icy worlds orbiting a distant sun can become cradles for life. The changes we have witnessed since Voyager are a tantalizing preview, a glimpse of the dynamic and complex world that awaits us. The greatest mystery is not what we have seen change, but what spectacular transformations and profound discoveries await when we finally send our robotic emissary to stay. And so we arrive at our final great mystery, one that points not to the past but squarely toward the future. The compelling and urgent need to return to Uranus with a dedicated modern mission. For decades, our knowledge of this tilted world has been frozen in time, based on a few precious hours of data from the Voyager 2 flyby and the distant, flickering glimpses from our most powerful telescopes. But the scientific community is now mobilizing for a grand return, with a flagship Uranus orbiter and probe mission standing as the top priority for planetary science in the coming decade. This isn't just about getting a better picture, it's about deploying a full scientific arsenal to a world that represents the most common type of planet in our galaxy, yet remains the least understood in our own celestial backyard. The core scientific goals of such a mission are as profound as they are diverse, designed to systematically dismantle every mystery we've explored. First and foremost, an atmospheric probe will be dispatched to plunge directly into the blue-green veil. This sturdy, heat-shielded instrument package would do what Voyager could not: taste the air directly. As it descends through the cloud layers, it would measure the precise abundances of hydrogen, helium, methane, and the elusive hydrogen sulfide, finally confirming the composition of the deep atmosphere and solving the puzzle of the missing ammonia. It would trace the temperature and pressure profile with extreme accuracy, revealing the hidden structure of the thermal inversion layers and pinpointing the exact level where methane condenses into snow. Most critically, it would hunt for the noble gases like neon and krypton. These inert elements are cosmic time capsules, preserving a pristine record of the specific materials from which Uranus formed. Their ratios would tell us definitively whether the planet was born in its current, frigid location, or if it was violently scattered outward from a warmer cradle closer to the Sun, finally resolving the great debate over its origin. Meanwhile, the main orbiter would begin its long, intricate dance around the ice giant. Its suite of instruments would be a technological marvel, a generation beyond anything Voyager carried. High-resolution cameras would map the surfaces of all 5 major moons in stunning detail, searching for fresh cracks, frost deposits, or signs of recent cryovolcanic plumes that would betray the presence of those hidden subsurface oceans. Spectrometers would analyze the composition of their dark and bright terrains, identifying the mysterious sooty material on Umbriel and the fresh ice on Ariel's canyons. But to truly see beneath the surface, the orbiter would employ a powerful radar sounder. By sending radio waves through the icy crusts of moons like Teutonia and Oberon, this instrument could measure the depth of the ice and potentially detect the reflective boundary of a liquid water layer underneath, directly confirming the existence of these alien seas and measuring their depth for the first time. The investigation of the planet itself would be equally revolutionary. A magnetometer would spend years mapping the chaotic, wobbling magnetic field from every possible angle, creating a full 3-dimensional model of its structure. This data would act like a medical scan for the planet's interior, allowing scientists to reverse engineer the dynamics of the dynamo generating it. Is the field born in a shell of superionic water ice or within a distinct layer of liquid water ammonia? The precise shape and variations of the magnetic field hold the answer, revealing the hidden flows and conductive layers deep within the slushy mantle. Furthermore, by carefully tracking the orbiter's path through the Uranian gravity field, scientists could map the planet's internal density distribution with incredible precision. This would tell us how its mass is layered, the size of its rocky core, the extent of its icy mantle, and the thickness of its gaseous envelope. This single measurement would solve multiple puzzles at once, explaining the planet's lack of internal heat by revealing if its interior is stratified and stagnant, and confirming whether a colossal impact truly did blast away its primordial energy. The urgency for this mission extends far beyond the curiosity about a single world. Uranus and Neptune are the only class of planet in our solar system we have not orbited. As astronomers discover thousands of exoplanets around other stars, they are finding that worlds the size of Uranus and Neptune, so-called mini-Neptunes, are among the most common in the cosmos. If we hope to understand the formation and evolution of planetary systems across our galaxy, we must first fully comprehend the 2 examples we have in our own backyard. Uranus, with its extreme tilt, its complex moon system, and its mysterious interior, serves as the perfect laboratory for testing our theories of planetary science. The data we gather there will not only rewrite the story of our own solar system's turbulent youth, but will also provide the essential context for interpreting the faint signals we receive from distant worlds light years away. The journey will be long, requiring a flight time of over a decade and leveraging gravitational assists from Jupiter to reach the outer darkness. But the scientific payoff would be immeasurable, transforming Uranus from a distant, enigmatic point of light into a known world, with its climate cycles understood, its interior mapped, and the habitability of its moons assessed. We would witness for the first time the changing of its seasons from orbit, watching as the slow roll of its axis triggers global storms and reconfigures its atmosphere. We would not be mere flyby tourists. We would be long-term residents, patient observers unlocking secrets that have been held in deep freeze for 4.5 billion years. This final mystery is therefore a call to action, an invitation to the next generation of explorers to complete the voyage that Voyager began, and to finally bring the enigmatic ice giant out of the shadows and into the light of understanding. From its profound sideways tilt to the whispered possibility of hidden oceans beneath the crusts of its moons, our journey through these 25 enigmas reveals a world that is anything but a simple, frozen sphere. Uranus stands as a testament to the sheer diversity and strangeness of our solar system, a cosmic reminder that for every question we answer, a dozen more emerge from the shadows. Each mystery, from the faint crackle of its chaotic magnetic field to the fleeting fury of its dark spots, is a thread in a grand tapestry of planetary science, woven with the violence of colossal impacts, the subtle dance of gravity, and the deep, enduring chill of the outer void. What these puzzles highlight is not just our ignorance, but our profound potential for discovery. The very fact that we can identify and ponder these questions from across billions of miles of space is a triumph of human curiosity and ingenuity. It means our models of planetary formation are incomplete, our understanding of climate dynamics is limited, and our search for life must extend into realms we once considered utterly inhospitable. Uranus challenges us to think bigger, to question our assumptions, and to recognize that the most common type of planet in our galaxy is also the one we understand the least. This isn't a conclusion, but an invitation, a call to the next generation of explorers, engineers, and scientists to pick up the torch and illuminate the darkness that still surrounds this tilted giant. Now we turn the question over to you. With so many bizarre phenomena to choose from, which of these Uranian mysteries captures your imagination the most? Is it the cataclysmic impact that knocked the entire planet on its side, the potential for hidden, life-hosting oceans on moons like Titania, or the bizarre, stuttering radio whispers of its lopsided magnetosphere? Let us know your favorite in the comments below. We read every single one and love diving into these cosmic conversations with our community of fellow space enthusiasts. If this journey into the unknown sparked your curiosity, please show your support by liking this video and subscribing to the channel. Hit that notification bell so you don't miss our next adventure as we continue to unravel the greatest enigmas of the cosmos, from the dust of Mars to the heart of distant black holes. Thank you for watching, and as always, keep looking